Annyeonghaseyo. Ohayo gozaimasu. Buenos dias and good morning to everyone here. I'm very happy to be here. I appreciate the opportunity that Katrina gave us to present this talk here in LA today. The talk is called From Embeddings to Transformers, How LLMs Work Under the Hood. This is a very interesting topic, and we are going to discuss it from a high-level perspective, but deep enough that you can conceptually understand what these large language models are doing under the hood. My name is Daniel Herrera. I'm a developer advocate at Teradata. And one of the things that I enjoy the most about my job is that I get to experiment a lot and to research a lot, not only about the great technology that Teradata launches and releases very often to our customers and to the market in general, but also regarding data-related technologies that are very important for our company and our customers. And of course, generative AI falls on this category. As I was coming here from the Netherlands, I was in a long flight, so I was watching some of the entertainment that they had. One of the shows was this magician. It's a Dutch show. And this magician will perform a magic trick to maybe one or two people. And then he will proceed to explain how the trick worked to the audience that he performed the trick for. And after all that we have heard about generative AI today, all the amazing use cases that we have hearing about that almost look like magic to us, I hope that this session for you is kind of like that second part. See a little bit what the trick is about. So let's start. As we know, generative AI feels like magic, but it might have some shortcomings. And that's natural in all technology. We have trade-offs that are made when we are developing a solution, and we have to live with certain shortcomings in one area to get the results that we want in another. And generative AI is not the exception. Understanding how generative AI works under the hood is important because we are able, when we understand this, to plan ahead and know how to gauge about certain shortcomings. So we are able to have the chill to accept that generative AI has limitations. We will have the guts to use it where it makes sense, but also, and more importantly, the wits to know the difference. And let's start by the most foundational concept. That is language models. Language models are not new. We have been interacting with language models since a long time ago. The translation app that you use on your vacations when you visit a country where you don't speak the local language, that's a language model. The text prediction software that you have in your cell phone and smartphone, that's also a language model. And of course, the assistants and chatbots that we love and we use every day are also language models. So a language model is nothing more than a system that is able to find patterns in human language in order to be able to analyze it and generate it. And there are two main tasks that we have to solve for when we are developing a model like this. We have to have a way to model words of the language, and we have to have a way of model the context. That's basically identifying the patterns between words. Modeling words is actually very easy. We can have several different approaches to model words. We can have very naive approaches, which are basically just having an ordered list of all the words in our vocabulary and assign a key to them. And that could be a way of modeling words. Modeling context, that's tricky. And the way of modeling context could go from a very simple approach to very complex approaches. So we are going to start building our first large language model with a small language model, very, very small language model, that will have a vocabulary that is very short. It's just a nursery rhyme and only in the first stanza. Mary had a little lamb, its fleece was white as snow, and everywhere that Mary went, the lamb was sure to go. Let's say that that was all the vocabulary that our language has. And we want to build a model that when we input one of the words in that vocabulary, is able to tell us what is the next word. The simplest way of doing this is that we can just count how many times the input word appears, and then we also make a count of what is the words that follow it, and then based on that ratio, we build a probability distribution. In this case, our input word appeared twice, Mary, and it's followed by the word had and the word went, respectively. So each of those two words have a 50% chance of being the next word when the word Mary is input, according to this very simple model that we're building. We can do that for the entire vocabulary, and that will give us this matrix. So we have on the columns the entirety of our vocabulary, on the rows the entirety of our vocabulary, and our probability distribution. The size of the probability distribution, of course, in this case, is a square of our vocabulary. Is it great? Is this model great? Well, it's not really great, but it's a good illustration. And I want you to pay attention to something here, is that a language model at the end will look a lot like this, even the large language models that we use today. We will have a vocabulary, and we will have a probability distribution of what is the next word. And disregarding the size of the model, the ending game, the endgame matrix that we will have, will look something like this, of course, much bigger, but it will be a probability distribution of what words follows another. Now, can we do better in this model that is not that robust? We are doing, at the end, only word pairings, right? We could predict what is the next word that follow another pair of words, right? So we have triplets. And we actually could do that, and this would be kind of the result. I restricted the vocabulary a lot, and I will explain why. It's because when we start to add more words as context in this type of modeling, which is called an n-gram model, by the way, the size of our probability distribution grows exponentially. Originally, we have our vocabulary square. If we try to model what's the word that follows a pair of words instead of one single word, then it's going to be our vocabulary cube. And if we want to do the fourth, then it's going to grow up in that fashion. So it's not very efficient, and it's very hard to scale. What our large language models that we have today have found a way to do is a way to embed context in a much more efficient way. And that's what this talk is about. And they do this by solving these three problems, essentially. Finding a way of representing the word, finding a way to incorporate the context, and finally, predicting the next word. And we are going to walk through right now across all of these three problems. Word embeddings, the way of representing the word. Embedding sounds like a fancy concept that is complicated and very mathematical, but it's actually quite easy to understand conceptually. Think of the concept of a tiger. And when you bring this concept in your mind, there are other concepts that will appear by the mere fact that you are thinking about a tiger. So it will be that the tiger is big, that is a feline. Canine? What does canine has to do with a tiger? You might think immediately. Well, of course, all carnivores have canine teeth. So canine has to do with tiger, not as much as big and not as much as feline. Now let's continue with this mental model and we are going to quantify how much feline, how much size, and how much canine this concept of tiger has embedded onto itself. So, of course, let's say that we have a lot of size, because the tiger is big. Let's say that we have a lot of feline, because, of course, it's a feline. But canine is just a little bit canine, because it's only for talking about the teeth the tiger has. Having this way of representing the concept with these quantifications of how other concepts are related to it is, in essence, what embeddings do. Of course, if anyone here in the audience is very knowledgeable about data science and have been working in this space, would tell me, well, we don't know exactly what each of those embedding dimensions is. You are just calling in size, feline, and canine, but we don't know exactly what that is. I know that, but we can build a concept, a conceptual baseline from this type of illustration. Also, we are not working with specific words. We are working with tokens, which might be words, but might not be words, might be combinations or certain aspects of words, like endings. But we are going to abstract away in this talk about these details. So we're going to be talking about words, and we are going to be thinking about these dimensions as related concepts to facilitate the illustration. Now, once we have this quantifiable representation of the word, then we can do very interesting things. Think about this. We could perform mathematical operations. So say that we have the representation of the tiger there, and we want to subtract. From the size, we're going to subtract 6, for example, and we're going to leave feline and canine just as they are. That will give us as an output another representation over there. Can anyone here guess what that representation will be? What is the word or concept that is related to our result representation over there? Can anyone venture a guess what that could be? Cat, we have to cat? Yeah, that's precisely what it is. And then, if we do other type of operation, we can have size, but we are going to subtract from it right now. We are going to subtract all of the feline, and we just add a lot of canine. What do we get? A dog. Depending how much size we subtracted, we can think about a wolf also. But yeah, it's a dog. And this might seem as a toy example, but you can go to download some sample embeddings that are available in the internet, and you can play with this kind of thing. You can have the concept, the embedding for king, and you can subtract the concept, the embedding from men, and what you will get is the embedding for? Exactly. So this is actually how it works, and you can experiment by yourself. Contact me if you want. I can send you the sources where you can get those embeddings. Now, other thing that we can do once we have these mathematical representations is that we can have them represented in a space. And of course, we are working with very limited space here, only 3 dimensions, because 4 dimensions, my mind is not as good. So let's put it in this way. We can figure out what concepts are more closely related to each other. And how do we do that? We do that by a very simple mathematical operation that's called the dot product. So we are just going to multiply all of the dimensions in each of the representations against each other, and the result will tell us how the words are related. If the result is very big, the words are very close to each other. If the result is a small number, then that means that the words are not very related to each other, according to this space representation. So in this case, we have that, of course, the tiger and the cat have a dot product of 84, which is quite high. Of course, they are very highly related. The cat with the dog have a dot product of only 30, so that tells us that they are not very related to each other. And the wolf or dog and the tiger have a dot product of 46 as a result. So they are not also that related to each other, though more related than the cat and the wolf. Of course, all of these values that I have for the representations are arbitrary, but yeah, you get the point, I guess, that this is a very interesting operation that we can have. Now, I want to bring you back to how you can apply this stuff in your daily work. And you have been hearing about RAG and all of these things that our large language models do. Well, basically, you can build indexes based on this, right? If you have a question from someone and you have your knowledge base, you can build the vector representation of your knowledge base by different chunks on different fragments. And then you can compare with the vector representation of the prompt of your user. And the more aligned that they are, that means that most likely the answer might be there in that chunk of your recommendation. So more on that can be found in other sources, and you can contact me for that as well if you're curious about that. But that use case is facilitated by this property of the word embeddings. Let's move forward. Now we are going to move from these concepts that were very limited to a bigger space. So the embeddings of Llama 3, for example, from Meta, are not only 3 dimensions, are more than 4,000 dimensions. So this is very difficult to fathom in our minds. Of course, as mentioned, we don't know what concept or what property each of those dimensions might be capturing. But yeah, it's basically these more than 4,000 dimensions with a vocabulary of more than 100,000 words or tokens. So now you see why when you are playing with this, you need GPUs, because a CPU cannot manage this type of matrix very easily. Let's move forward. How does the context affect the word? This is the core of the attention mechanism, which is the core of this talk as well. So this is the part that excites me the most, and it's very interesting how it works. You might have seen a diagram of that in the original paper, but this is going to be much more simple. And if you go back to the original paper, attention is all you need. After going through this, you are going to get it much faster. Now, you might be thinking, OK, we have the embedding that already has all the concepts that this specific word is related to, right? So wouldn't that embed all the context we need to build our probability distribution? Wouldn't that be enough? And of course, we might think that it is enough. But we have certain edge cases. And in those edge cases are not really that edgy because it appears in most of the words. Most of the words have different meanings according to the context in which they are being used. Take these 2 sentences as an example. A python ate the mouse, and control your mouse with Python. Both of the words mouse and Python in these 2 sentences are very different in how they work. But unfortunately, the embedding that we have originally, that is the numerical representation of those words, is going to be exactly the same. Because the embedding is just kind of sort of averaging out all of the properties or concepts that relate to that word along all of the training data. So it's not going to help us to only have the embedding. We have to have a way to know from the context of the query where we are trying to predict the next word, what is the context in which the word is being used. And that's what the attention mechanism solves. How does it solve it? Allowing words to have gravity. In the first example that we have, the verb ate exerts gravity on the words mouse and Python, and is bringing those words closer to the animal dimension, because animals eat. And this is just conceptual. I will explain you how does the trick works here. But this is basically a result of the trick, right? We have gravity. The verb is pulling these nouns closer to certain dimension. In the other example, controls your mouse with Python, the verb control is exerting a lot of gravity towards the words, but along the other dimension. It's bringing them closer to control instead of being related to an animal. Of course, we're using just animal and tool here as illustrations. We know that the embedding space is much bigger, but that's the idea. Now, how do we manage to have these specific words to be able to exert this gravity, to pull the embeddings closer to certain dimensions? Any ideas? OK, let's get to reveal the trick. The trick is in 3 different matrices that we have. These are represented in the paper as the Q, K, and V matrices. These are no more than other embeddings that represent certain things. The query embedding represents what a specific word is looking for. So in the case of Python over here is a noun. So the query embedding most likely is telling we want to look for verbs or adjectives in our context. Of course, that word Python is not alone in the prompt or in the sequence that we're analyzing. So it's a Python ate the mouse, right? So they ate or control, which is in the other sentence that we have. This will have also other matrices or other embeddings that is the K embedding. This is for each of the words what that word is offering to all the other words in the context. So in the example here, Python is looking for verbs of adjectives, and the key embedding regarding the other words, in the case of ate, and in the case of ate in the first sentence, is offering a lot of verb. So they are quite aligned. Now, the value, which is the most important one, is defining how these other words that appeared in the input should modify the embedding of the word that we are analyzing. Simplifying it here, Python is looking for verbs. Regarding all the other words in its input, where we put a Python ate the mouse, ate is the verb. And what verb is contributing in this case is adding a lot to the animal dimension of the embedding space. Now, in the other example, have the same. Python is still a noun, it's looking for verbs. Control is a verb, but what control adds to the value is a lot of the dimension of tool instead of animal. So it's pull in the back. So it's basically a multiplication operation that managed to control this sort of gravitation procedure. Now you might be asking, how does the model know what the Q, K, and V matrices should be? The answer, as in a lot of stuff in this area, is that these matrices are learned during training. So basically, the model, when it's been trained on all the training data, will come with a weight of Q matrix, a weight of K matrix, and a weight of V matrix. And these matrices will modify each of the word embeddings that we have originally and will give us the vector for Q, K, and V. That is going to be used during inference. Now, this part, if you have any questions, you can ask me later on. I will pass from it now, because you might also see that there are several boxes there that might have called your attention. But let's continue, and you can ask about that one at the end. In summary, what the attention mechanism is doing is that you have the query, which is representing what each of the words in the input is looking for. You have the K, which is representing what each of the words in the input is offering. And you have the V, which is how those words in the input will modify each other. Now, the quantification of how much of that V is going to be added to the final result of attention is given by our old friend, the dot product. So if the queries from one word are very highly aligned with the keys of another words in the input, that value is going to be high, and that value will multiply the value matrix for the final attention result for that specific word. And the end result that we will have is a different embedding of each of the words in the input that is already modified according to its own context in that specific scenario. We have the much improved embedding, and we actually completed the attention mechanism. We just have to predict the next word. And as we mentioned at the beginning of our talk, we have, at the end for making the prediction, what we need is a probability distribution over the vocabulary on what should be the next word when one word is the last one of one input. But what we have right now is this other matrix over here, where we just have a modified embedding, basically. Just is the original embedding of each of the words with modified features according to the result of attention mechanism. How do we go to predict the next word with this output of attention that we have here? The answer, again, is linear algebra. And it's another matrix. We have a weight and a result matrix that multiplies the result of attention that will output the probability distribution we need at the end. And this weight matrix that we have at the end is also learned during training. So that's basically the way that we modify from where we were, which is the attention result, to the probability distribution. And we end up with our nice prediction here with a Python 8D. Mouse is the most likely result, and control your mouse with Python is the most likely result. In summary, and this is kind of like the slide that captures the entire thing, we start with word embeddings, which are the numerical representations that relate each of the words in the input to a specific set of numerical values that represent the word. We have the weight matrices that help us to produce query, Q, K, and V embeddings that basically tell us how the words relate with each other. And then at the end, we have the matrix that help us to have that transformation, the final one, that just brings the probability distribution back. There is something that I didn't tell you that I kept until now, because if you remember the first slide, said that the embedding would represent what and where is the word. And we have not talked about word location. And actually, this is part of the magic of the attention mechanism. It doesn't care what word is coming in what order. It basically adds a modification of the embedding at the beginning in order to order the words. The reason it does that is that it's very efficient during training to just treat all the words equally without regard to what word comes first and what word comes last. We care about the last word only when we're making prediction during inference. But during training, we don't care. We just treat them all the same. Because during training, we are predicting the next word even when the training data is this sentence, for example, a Python 8 mouse. The model will be trying to guess what is the word that follows A. Then it will be trying to find out what is the word that follows a Python, and then so on and so forth. So there are different stages there for training and for inference on how the mechanism works. Now, moving forward to the summary, I wanted to close with this quote from Mr. Jan LeCun. And I really like it because it really frames this technology very well with mainly 3 points that he's making there. LLMs cannot answer questions whose answers are not in the training data or the prompt itself. That part, or the prompt itself, is very important because that's what allows us to do RAG. We are sending the potential answer in the prompt and telling the model, hey, find the answer, but from here. LLMs cannot acquire new skills or knowledge without human intervention. And this, I think, personally, I think that's very important because we tend to forget it. If the model can generate images, it's because a human drew that image first, and it was using the training data. The model is just taking what was in the training data and processing it. And LLMs cannot invent or create. So that can give you a framework on what could be good use cases. And the good news is a lot of good use cases you can implement with your own data. In Teradata, you are able to bring this technology to your data with different strategies. It's very useful to perform data labeling, relying on large language models. And sometimes you need only a small model for that. You can do that in database with bring your own model. If you want to use something that's a little bit more complex, and you are in Vantage Cloud Lake, you have Open Analytics Framework that allows you to import a pre-trained model from Hugging Face and use that against the data that you have in your database without your data in your database ever leaving. And finally, we have a lot of model endpoints. If you need something that a foundation model that is huge from Meta or OpenAI or other cloud provider might offer, you can also integrate that with Teradata through the Model Endpoint API. But of course, how to implement the use case is on you, but we are here to help you. Thank you very much.
That was great. That was great. All right, we have a few minutes for questions. I loved how you broke that down for all of us. Questions about any piece of it? Yes.
The gentleman.
He's coming. Just gotta.
I apologize.
Sorry.
When I change languages from English to Greek,
Yes.
The order and sequence of words are different. Is that resolved in the training, or is it a different model?
Okay, let's go back. You are asking a lot of the things that I left out, but that's very, very, very insightful. So the answer is, when you are doing translation, the architecture is a little bit different than when you are doing only generation. Only generation models are able to do translation, and when these only generation models, like the one that is used for GPT or Llama, are doing translation, the order doesn't really matter because in the training, all of that is solved in training, so as your second statement. But there is another strategy that is the models that use an encoder and decoder architecture that are used for language translation, and actually the attention is all you need paper is based on that type of architecture because it was in a translation scenario. In that case, the order might be relevant in one aspect of the decoder and encoder. So the process does vary, but in the ones that are purely text generation, which can do translation, the order doesn't matter over training. It's basically just like this.
So both. Other questions? No other questions? All right. So the one question, and I like that a little bit of trivia. In addition to word embeddings, what's required? What's required? In addition to the word embeddings, what's required? Context, which happens through gravity. Can you go back to that slide where you had that?
This one. Okay, the summary.
Yeah.
Great.
Does that make sense to you guys? Kind of, sort of? Okay. Questions? Any other questions? Let me ask this question of you guys. How many of you are using or applying large language models today in any capacity, outside of you just asking questions of it as a consumer or educational perspective? Yeah? Do you have an example?
I'm from Qantas Loyalty.
Yeah.
But in the airline side, they are evaluating these models and testing some out for, I think, to help with the like the call center agents. The call center agents,
Okay.
service center and call
Oh,
center
sure.
agents, to kind of filter down complaints and try to rank them based on, say, I mean, some of the ones that are
Urgency
more
or
urgency,
severity,
criticality,
like,
et cetera,
hey,
yeah.
my flight just got canceled,
Yes.
help me. Yeah.
Those are the ones
Okay.
we use.
Any response or any learnings from starting to use that?
I think they are being a bit more cautious now because there's a, I'm not sure if it's more for generative AI or for large language models.
Sure.
But in some cases, I think one of the things that I heard was, and I'm not sure if hallucination is kind of relevant to LLMs or not. Is it more generative AI?
Okay, can I take that one?
Yeah.
Yeah, hallucinations are basically generative AI is implemented through large language models, so that would be the relation there. Now, the part of hallucinations that we didn't talk about is, of course, the model is just trying to build a probability distribution according to what the model has. So the model cannot tell you what you are asking me is not in my training data, because that escapes what we all discussed. So what the model will try to do is like a child that kind of like cheats in the exam, like didn't study, but wants to answer the teacher, who will just come with a plausible answer to the question you are making. And it will sound convincing because he's a very smart child. He's very smart, but it might not be true. So that's the essence of what hallucinations do. Now, how you can kind of mitigate a little bit of that? What do you do with a naughty child that doesn't want to study? Two things. Either you allow him to cheat in the exam by providing him all the answers. And then you tell him, okay, this is the questionnaire, this is the content that will come in the exam. Memorize that, and then you ask him a question, and he will just remember, oh, the questionnaire was that, and bring it back. That's RAG. He's providing the naughty child with a questionnaire with the cheat sheet of what he should answer. And if he doesn't find it in that cheat sheet, you might have a better chance that he will say, I don't know, because it was not in the tool that you give me. So that's RAG. The other part is kind of like forcing the child, no, mister, you are going to the library and learn. That's fine-tuning.
Great example. Any others? Question down over here.
So on one of the slides, it said LLMs cannot create.
Yes.
Just trying to understand what that means, because if you use, like, let's say Meta, ChatGPT, and you ask it to write some piece of poem or, a thesis about something, would you not consider that as a creation, or how do you feel about that?
That's a great question. It's a lot more philosophical than technical, and we can discuss several perspectives on that. I tend to agree with this because everything is based on the training data. But then you might retort to me, okay, how much of Star Wars is possible because Isaac Asimov wrote the foundation in the 50s with the Galactic Empire and everything, right? Wasn't George Lucas creating? So isn't that what the large language model is doing? So it's a philosophical question that I don't think I can answer, but I tend to be in this camp.
That was a great question. I was kind of thinking about that as well. I'm like, well, But I think the premise is it can't create something outside of what's already been provided as a part of it, right?
Yeah, exactly.
Okay, great. Other questions?
Just a follow-up to the earlier part that you were saying is like that naughty child. That was a great example. But of course, the training takes a lot of time. So if it can't answer the question based on what it's trained on, it can't start training in real time, so it probably needs a lot of time? Or is this something that you can say, I don't know the answer, and suddenly it goes to a knowledge base relevant to the question and tries to learn and come back? Or does that take a lot of time, so you have to kind of do a lot of training upfront?
Okay, that's an interesting question. I will put the programmer hat now. I think that would depend on how you want to structure your application. The problem is that you cannot do it that way, because if you are using just the pure LLM without the retrieval augmentation system, the LLM will not be able to tell you, I don't know, because according to the mathematics, it will just come with the best answer that it can find. And the opposite you could do is kind of like providing the retrieval augmented system. You provide all the potential context first from a vector database, which Teradata will implement very, very soon. And you bring it back. The model will, in that context, try to answer your question because it's contained in the prompt. You can instruct it in the prompt. If you don't find the text or something relevant in this text, just tell me that you don't know. And then maybe you are using a smaller language model for that part, for just doing the vector analysis. But if it doesn't find anything there, you can try to send an API call to one of the bigger language models that are trained on more data and try to get an answer from there. But the problem there is that one might also hallucinate, because we don't know. They also don't have an infinite data, right? So it's a risk.
Great question. We have time for one more. One more question? Okay. We'll close it out.
Yeah, close it out. I just want to have a final message. For those of you that are more technically inclined, you can scan that QR code there. This is a repository that is based in one from Andrej Karpathy, which is one of the founders of OpenAI. And that repo walks you through creating your own large language model that basically generates text based on Shakespearean English. With the parameters that I have it configured right now, you can do it in CPUs. I have done it in my computer. The Shakespearean English is not very Shakespearean, though.
Well, here's the other thing. Then they can use BYOLLM to bring it into Vantage if they choose.
This one, you could export it to Onyx later, but this one, because it's more tailored to be more kind of like didactical and educational, so basically it's for having you kind of like do it in real time in your computer to kind of like follow the other part that I didn't explain, right? Because I explained all the linear algebra part. The learning is a lot about the calculus part, and the calculus I didn't touch at all. So for the ones that want to delve into the calculus, they can go to that one. And if you want the use cases, which is the exciting part and goes for what Trina was doing, scan that other QR code, and there are a plethora of generative AI use cases in ClearScape Analytics experience that you can implement right now with Teradata.
Great references, great resources. You guys join me in thanking Daniel.